Citric acid is one of the world's most important organic industrial chemicals, with nearly 2 million tons being produced globally every year. It is widely used across the food, beverage, and pharmaceutical industries. In this project, we aim to utilize the fungus Aspergillus niger to produce food-grade citric acid via fermentation. Our design objectives are achieving a 99.5% purity product to meet food-grade specifications and producing 10,000 tons of citric acid per year. We also aim to design our unit with a carbon capture unit that captures over 90% of carbon dioxide produced by the process.
The bioproduction process can be broken down into 4 sections: fermentation, separation, crystallization, and carbon capture. The fermentation section is where we feed 1,000 grams per liter of sucrose syrup and a mutated high-yield strain of Aspergillus niger into our inoculation vessels. This process scales up the volume of inoculum to then be added to a 250,000-liter main fermentation tank where citric acid is produced. At the end of the fermentation process, the broth is filtered and enters a holding tank, which facilitates the transition from semi-batch to continuous operation. The separation process includes a concentrator, 2 active carbon columns, and 4 reactive extraction columns. After this unit operation, the medium will be decolored, deionized, and extracted as a pure aqueous citric acid solution. The crystallization unit then concentrates the aqueous citric acid solution and crystallizes it into anhydrous citric acid crystals in a continuous vacuum flash crystallizer. Lastly, the food-grade crystals are dried, packaged, and stored in an off-site warehouse. We also recognize a significant amount of carbon dioxide is being produced during inoculation and fermentation. To address this, we added a carbon capture unit that can capture more than 90% of the total carbon dioxide generated and liquefy it to be transferred and used for enhanced oil recovery in the region.
The main challenge of modeling a semi-batch process is accounting for the changing volume and fermentation reactions simultaneously. In order to address this challenge, we developed our own simulation software to best model this process. The current setup showcases a semi-batch process. The drag-and-drop equipment interface allows for ease of testing for any plant design by keeping track of various simulations. This software also displays time series data needed to optimize and design the plant. With this information, we are able to effectively model various parts of the bioproduction process to best meet the design challenges for this project.